In this video, we're going to do a review of the physical chemical changes with a focus on chemical reactions, how to represent chemical reactions as various types of equations, and also briefly how to balance chemical reactions. So let's start off with what chemical reactions are and then how we can represent them. Before you start this video or this lesson, I recommend you watch these preview videos here. They're really, really good crash course videos. They go over the main concepts you would have seen in grade 10 and even go into a bit more depth so you can understand what's about to come next. And it gives you it from a different perspective with some really good examples of the chemical reactions and these concepts at play. So please take a look at these videos. They're great. They have great examples to enhance your understanding. So we're starting off with what a chemical reaction is. Remember, it's a process where you have substances that interact, and when they interact, they're going to form new substances. So they have different chemical identities. And at the end of this chemical reaction, they typically have different properties. They have different chemical properties, for example. But the main point is that it does need to be a chemical change. So a chemical reaction is when substances interact, and in that interaction, they undergo a chemical change of some sort. They're a new chemical identity. And to represent a chemical reaction, rather than write a big paragraph or a big essay about it, we write a chemical equation. So it's a nice way to represent what's happening during a chemical reaction. And there's three main types. You can have the word, skeleton, and balanced. So here we have an example of a chemical equation that represents a chemical reaction. In this reaction, we have these two substances here interacting to form a new substance over here with a new chemical identity. We had N2 and H2, and they became NH3. So a few terms you need to know are reactants and products. Remember that the reactants are the starting materials, what you start off with, your ingredients, let's just say, and they're usually on the left side of your equation. And then after that, you make an arrow to show what's being formed or produced. And so what's produced or formed at the end there is your product or your products. You can have one product or several products. And it's typically on the right side of the arrow. So this here represents a chemical reaction. It's an equation that represents that. Reactants on the left, products on the right. And remember that chemical reactions, you need to spot when they happen. When you do a lab, there's several clues you can look for to see when a chemical reaction is occurring. And so if you click on these links here, you'll see a demonstration for each one of these sort of hints that a chemical reaction is happening. And when I say chemical reaction, we see a chemical change happening. So essentially, these are the clues of a chemical change. So you might see an unexpected color change that might happen. So you can view that demonstration here. You might see energy being released or absorbed. So you might see that in the form of a change in temperature, or maybe, so for example, the substances get hotter or colder, or you might see that as the release of light, like a glow stick, for example. You might see gas being produced. And I don't just mean like boiling water and heating it up. That's a physical reaction, a physical change. When this happens, you might, for example, mix, let's say, a solid and a liquid like vinegar and baking soda and see some bubbling, and that's gas being produced. It's a gas that's different from the initial reactants that you had. A precipitate might form, which is really just solid forming. So you can see that over here we have two aqueous solutions. That means they're basically compounds dissolved in water. And then when you mix them together, substance forms that it can no longer dissolve in water to the same degree, so it comes out as a solid, and we would call that a precipitate. So this is a yellow precipitate over here. And it often looks cloudy. If it's cloudy, it's a precipitate. Or sometimes you might have a change in taste or odor. We don't use that. We don't use taste in the lab very frequently, at least in high school. And also a change in odor. So you might have two substances reacting. They smell really gross at first. Then when you mix them together, they have very, very different smells. So in grade 12 chemistry, if you take that, you'll do an organic chemistry lab where you mix two substances together, and they don't smell good at the beginning. When you do mix them at the end, they can make smells like banana or mint. So a change in odor can also be an indication that you're producing something different or new. So we're going to do some examples of word equations and skeleton equations in our handout, but also in this slide deck here. So your word equation is a way to represent a chemical reaction using primarily words. We don't indicate the states in a word equation. We just put the names of the chemicals that are reacting, and that's about it. So for example, over here, you can see that we have carbon dioxide plus water, arrow, oxygen plus glucose. So the left side, again, are your reactants. The plus on this side essentially means reacts with or and. So carbon dioxide and water react, or you can say carbon dioxide reacts with water. And then the arrow means to produce. So to produce oxygen and glucose. That plus there means and. So we're going to do some examples of writing word equations together. And then we'll also do some examples of writing what's called a skeleton equation. So a skeleton equation is where rather than use words, you use the symbols and formulas of the reactants and products. And here is where you can actually include the states as subscripts. So remember, S is solid, L is liquid, G is gas, and AQ is aqueous, meaning dissolved in water. So in this example here, we can see a skeleton equation of a combustion reaction. And so you have this molecule over here reacting with this molecule here, oxygen, to produce CO2 and H2O. Notice they're all written in their formula forms. We have our gas there, our states are there as well. So those are all provided to us. There's different ways to figure out states, and I'll show you how to do that as we do some sample problems together. So generally, we can use our periodic table to figure out what the states of a substance will be when we're writing out the equation. Generally, anything on our periodic table with black font, unless otherwise told in the question, will be solid. So if we go to our periodic table, remember from either Unit 1 or Unit 2 calendars, it's in every calendar here. We click on periodic table. So anything with black font, we can assume is usually going to be solid in the equation that we're writing. And then anything with blue font is going to be liquid unless told otherwise. So if you take a look at your, oops, not here, let's go over here. If you take a look at your for example, bromine, mercury, they will be liquid when we're writing them down in an equation. And then anything with the red font is going to be a gas in our equation. So remember, most of our Hofbrinkels are gases. And remember that when you do write your Hofbrinkel elements down, the H, O, F, N, Cl, I, and Br, they do need to have a little 2 there. That's when they're alone, not in the compound. And then also, don't forget, we can also have aqueous. So aqueous will generally be when you have acids or bases, we'll put AQ. Also, if you have solutions. So generally, in a question, you'll be told that you have a solution of something. And if you have a solution of something, you have to put AQ, not liquid. It might look like a liquid, but in reality, it's dissolved in there. So if I have a sodium chloride solution, NaCl solution, that's not liquid sodium chloride. Right? Remember, sodium chloride is an ionic compound. It melts at about 800 degrees Celsius. So when you have a solution of that, it's just the solid dissolved in the water, and that's why you put AQ as opposed to liquid. So there is a difference between them. Then we're going to take a look at balanced equations. So remember, skeleton equations, they don't care if we're missing atoms on both sides of the reaction. But that goes against the law of conservation of mass, which we've seen previously. Remember that in chemistry, when you're doing a chemical reaction, whatever mass you start off with, you need to end up with. You can't destroy or create new matter. It's just you'll have it there, but in different arrangements as new substances, but it should still be the same mass. So the law of conservation of mass, sometimes called the LCM, basically says that matter can't be destroyed or created. So whatever you start off with, mass of your reactants, has to be equal to your mass of your products. So if we look at this example over here, we have a chemical in this test tube and a chemical in this flask over here. They haven't mixed yet, but the total mass of this whole thing is 67.25. When they do react, new substances are produced as the reaction occurs, but those new substances are essentially replacing the old ones. We're just rearranging what was already there in different ways, almost like rearranging Lego little blocks, for example. So we still have the same mass in the end. We didn't lose or gain mass, and that's the law of conservation of mass. So you can see that in this reaction over here. If I had some H2 and some O2 reacting, at the end, I might have different chemical identities, H2O and H2O, but notice that the number of atoms of each is still the same. So 4 H's total, 4 H's total, 2 O's total, 2 O's total. And that's a balanced reaction. That's what all reactions follow, the law of conservation of mass. You can't lose atoms or get new atoms from somewhere. You simply rearrange them. So a skeleton equation doesn't take that into consideration, but a balanced equation does. That's where you use those coefficients in the front to make sure you have the same number of atoms on the left and the right side. And so we're going to do some examples of that in the next video as well. So here we can see just an example of rearranging. Here we have sulfur and iron. Before they've reacted, we have 32 and 56 grams. That's a total of 88 grams of reactant. We then mix them together, and after the reaction, we have iron sulfide produced, iron 2 sulfide. Notice the mass here, it's 88 grams, which is what we had at the beginning. It's just a total of 88 grams. Sometimes there might be some gas that escapes if you don't put a lid on this, for example, or you don't collect it and it looks like you lost mass. But in reality, you didn't. You still produced that mass. You just let it escape. It's like spilling it and say, "Oh no, I lost some." You didn't really lose it or destroy it from the universe. You just spilled it. So yeah, assuming you capture everything, the mass should be the same. If the mass decreases, it's because you didn't capture everything. There was a leak somewhere and some of it leaked out, or you spilled something. But assuming everything is perfect, the mass should be the same. And so you can see that with these Lego blocks here. We have one red block, two yellow before they reacted. After they reacted, still the same amount of blocks. One red, two yellow, just arranged differently. This is a new chemical identity. A new chemical identity. So they should have the same mass. If these were 1 gram each, so 3 grams, this is still 1, 2, 3 grams. So you didn't lose any mass there. And that's what a balanced equation will allow you to do, to keep, to demonstrate or to follow the law of conservation of mass. So let's go ahead and do a few sample problems with our word and skeleton equations. And then in our next video, we're going to do some practice balancing. So let's go to our handout here. So what did we see today? We saw that chemical reactions is when you have substances interact to produce new substances with a new chemical identity, and they have different chemical properties. And to represent it, so essentially a chemical change happening when those substances interact. And to represent them, these chemical reactions, we use a chemical equation, which can be a word, skeleton, or balanced equation. And we saw that in a reaction and in the equation, you're going to have two main parts. You're going to have reactants, which are the things you start off with, and they are on the right side, sorry, not the right side, the left side of the arrow, as you can see in the red over there. So the left side of the arrow, here are my reactants. And then the products, they are what's made. They're on the right side of the arrow. And so they're what's produced or what's made on the right side of the arrow. And please make sure you do put an arrow, not equals, because these N2 and H2 are no longer equal to NH3. NH3 is different identity from N2 and H2, so putting equal is technically incorrect. You do have to put that arrow. And then we saw that there are some clues to when chemical reactions occur, chemical changes. And so you can click on each of these links there to see some demonstrations of each of those clues. But we saw color change in energy, which could be something getting hotter or colder, like the temperature change, or energy released as light, like a glow stick. We saw a gas could be produced, and that's, for example, you'd see that as bubbling, not babbling, bubbling. A precipitate can form, which is essentially a new solid that forms in the solution. A new solid forms, solid chunks. In fact, if you let this settle at the bottom eventually, it'll look like sand at the bottom of water. So you'd see a bunch of yellow solid just sitting there. And actually, you could filter it out too if you wanted to. You could put it through a little filter and collect the solid. You might also see a change in taste and also odor. Those are different clues that you might see. And we saw there's different types of chemical equations. Word equations, which identifies the reactants and products by names or words. And we don't use states for these typically. We saw that there's a skeleton equation where you use symbols and formulas instead. And there you can use the states as subscripts. In the word equation, we didn't use the states. So for example, here we had carbon dioxide and water. This means and or reacts with to produce oxygen and glucose. And we didn't put the states there. But once we get to the skeleton equation, you can put the states, the solid, liquid, gas, or aqueous. And so you can see that in this example over here. And then we saw that a third type of reaction or equation, is the balanced equation, which actually follows the law of conservation of mass. Basically, we need to have the same number of atoms on both sides. So for example, here I have 2 O's, here I have 2 O's, here I have 4 H's, here I have 4 H's. And so we need to make sure that we follow that, and the only way to indicate that in our equation is by balancing the equation using our coefficients. So essentially the balanced equation is like a skeleton equation. It has symbols, formulas, states, but the only thing that we do is we add the coefficient in the front. And then we saw that to predict if you had solid, liquid, gas, or aqueous, You could use your periodic table. So anything in black font is solid, blue font is liquid, red font is gas, unless told otherwise. And for aqueous, those are things like acids and bases, or if we say you have a solution of something. Later on, there'll be a way to predict if you have a solution or not, but for now, for the most part, you'll be told if you have a solution. And then we'll get to balancing. I'm not going to do a very long review of balancing. I might do one or two examples because you've seen balancing before in several videos. You've seen it in grade 10, and we've already reviewed it in the chemistry review package. If you do have some trouble going over balancing, just do make sure you go back and review those videos. And you can take a look at all the answers here for these different balancing questions just to get some more practice. I highly recommend you become really good at balancing because you're going to need to balance as a basic skill for Unit 3 especially. So please make sure you are practicing that balancing. We'll do one balancing example actually, and then after that we'll end the video and then restart a new video to do some combination of problems. So let's go ahead and try P4O2 react P4O2 react to produce P410. So we want to have the same number of atoms on both sides. My P's look good, but my O's don't look good. I have 10 on the right and 2 on the left, so I can simply put a 5 over here, and that will give me 10 O2s, because it's 5 times 2 is 10, and my P4s are good. So now everything is balanced. 4 P's, 10 O's, 4 P's, 10 O's. Same on both sides. Sometimes you might have polyatomic ions present. If you do, treat them like a single unit, and that makes your life a lot easier. So for example, on the left side I have 3 nitrates. On the right side I have 1. So let's put a 3 here. Now I have 3 nitrates and 3 sodiums. Okay, well, you know what? That probably wasn't the brightest thing to do, because notice I have 2 sodiums on this side, so that won't really work out. So I need to choose something else that'll work for me here. So what I could do is I could put a 3 here. That'll make 6 sodiums. That's okay though. What I'll do is I'll go back and I'll erase this, and I'll put 6 over here. So now I have 6 sodiums. 6 sodiums, 6 nitrates. Over here, so I have 6 nitrates as well. So to make 6 nitrates here, I can put a 2 in the front. It gives me 2 aluminums and 6 nitrates now, because 2 times 3, 2 times 1, 2 aluminums there. And now I think, oh, this is all balanced. So it worked out that way. So notice that, if it doesn't work, you go back and forth a little bit until you can get something that works out. Again, here, what made things easier is I treated my nitrates as individual units. So NO3 was its own thing, and NO3 was its own thing on the other side as well. So polyatomic ions repeat, you can treat them as their own individual units. And so you can go ahead and try the rest of these balancings out, and the answers are all provided so you can check your work. It takes a little bit of refreshing, but you can go ahead and practice that. You'll notice that the big number you put in the front is called a coefficient that multiplies everything within the formula, and the small number is called the subscript. The little number is called the subscript. Where there is no subscript written, we know it's a 1. And remember, you cannot change the subscripts. You can only change the coefficients when you're balancing the equations. Here we have some general tips that you can use when balancing that usually help. And I'm just going to state it again. Never change the subscripts, only change the coefficients. And just to mention, if you want to see a little bit more of a review video for balancing, you can click on the link on your handout over here, and that'll lead you to some more review videos for balancing, just in case you need a bit more practice with that.